I'm Jonathan Speed. I'm a magnets engineer at CERN. I work with the design and analysis and procurement of accelerator magnets that we use in some of our particle accelerators. One in particular, I'm predominantly working on one of the upgrades that we're doing at the moment on one of our particle accelerators.
So what is it that you're upgrading?
So they're looking to increase the energy and also increase the luminosity of the accelerators. So the luminosity is a bit of a physicsy term that engineers often struggle with, but essentially what they want to do is increase the number of interactions between protons when they finally collide the protons in the various experiments. So essentially, if you have a more dense bunch of protons, then more of them will collide. So in a given time period, you'll get more collisions and therefore more data. So one of the key things they want to do is increase the amount of data they're getting out of it.
Yeah.
In order to do this, some of the accelerators need to operate at a higher energy level, which generally means higher magnetic fields. And then they also want the beam itself to be denser and occupy a smaller space. So if you want a tighter beam, that usually means higher field qualities so that the beam doesn't start expanding.
So are those the parameters that you're looking to optimize?
Yeah, there are key parameters in all the magnets is the field strength or the field gradient, depending on whether you're talking about quadrupoles or dipoles or sextupoles, so on. But yeah, it's mainly the field strength, in particular the integrated field strength. So we care about how much magnetic field the beam sees as it passes through a magnet. And yeah, of course, the field quality is very important for us. You have a beam that's of a certain size, you want all the particles within that beam to see exactly the same field.
And you use Opera to help with the design?
Oh yeah, the design, certainly the magnetic design is predominantly done using Opera. So right from the start, we tend to do a few analytical calculations to get a rough overview of how the magnet's going to look, and then it's quickly into Opera 2D in some cases, or sometimes even straight onto Opera 3D, where we can really start to focus on the pole profile and where the saturation of the magnet's going to lie, how big the return legs need to be in order to have the magnetic flux going efficiently around the iron. Things like end chamfers become very important in 3D. So along the pole length, you could in theory just have a right angle when you reach the end of the magnet. But then in the integrated field, this often starts to introduce certain errors. So we often focus a lot on how to reduce the errors that come from the end angle of the magnet as the beam leaves the magnet. That's the area where you often get the most errors.
Is there a particular feature of Opera that you use the most, or that is the most important for doing this?
I think one of the big appeals for us of Opera is the way it deals with non-linearity of the BH curves and the saturation that you get in parts of the iron that we've generally found with Opera that it can model this very accurately. You can get a very accurate simulation of what goes on in a small corner or a small shim or something like this that's become highly saturated, and you can see how this varies with energy levels, which with certain other software out there, you start to find that as you get into highly nonlinear areas, the results can become a little less accurate and so on, whereas Opera tends to stay pretty true to the real world in that sense.